Okay, so now the third one, the band pass filter, we have that here. You can see the same frequency response, and what you can see is basically it allows the frequencies within a lower and upper cutoff to pass. That's called the pass band, and the other two are the stop bands. And how we're going to be implementing this is there are one op amp, two op amp, and there's something called Salin key. There are many configurations for implementing this, but what I'm going to be doing is a simpler one, I guess. It's just a cascaded. Basically, if you see this part of it, if you see this half, it's sort of like a high pass filter, right? It's allowing the higher ones to pass and attenuating the lower. And this till here you can see is sort of like a low pass filter. So basically, if you cascade a high pass filter and then give that output to a low pass filter, you will create a band pass filter. So you can do it with two op amps, and you just create the same one op amp circuit what we did for high pass and low pass, and just feed one's output to the other one. So that's what I've done here basically. This is the high pass filter stage, and this is the low pass filter stage. And since we know this op amp anyway, the 072 has two op amps inside anyway, so we can just make use of that. So the two cutoff frequencies what I've designed for is 4.5 kilohertz and 5.9, because basically I wanted 5 kilohertz as the center frequency and that to pass. So yeah, I've chosen 35 nanofarad and 1k for the input side, and this one 2.7k and 10 nanofarad. So yeah, that's how this is done. Rest of the circuit remains same. So yeah, let's see the breadboard circuit. And yeah, we have the circuit ready here. Just changed a bit of the wiring, and yeah, basically to get the 35 nanofarad I just had to put 22 nanofarad in parallel with 10 to achieve that, and rest of it remains same. And now the all the both the op amps are used, and yeah, so now we'll give the 5 kilohertz sine wave. And yeah, you can see currently the output is the final second op amp output is basically around 3.5 volt peak to peak, right? So let's maybe move lower. Let's go to 3 kilohertz, and you can see it's become 3.3. It's reducing, and as I further reduce it to now 2 kilohertz and now 1 kilohertz, it's further reducing. And and finally, let's say we go to something like 900 hertz, so on and so forth. You can see this is decreasing on and on, which proves that the it's now in the attenuation region. And now let's see the high pass side, right? So now let me increase this back to 5 kilohertz where we were at before, and it's 3.5, right, as seen before. So now let's increase it to 6, and you can see it's become 3.4. And further, if I reduce it to may increase it to 8 kilohertz, 3.05, and at 10 kilohertz we have 2.7. So you can see it's starting to almost get fully attenuated. And if we keep going further, maybe something like 15 kilohertz, yeah, 2.1, and so on, same as before, it will continuously keep decreasing. And that proves that it's acting as a band pass filter. That means centered around the center frequency of our 5 kilohertz basically, we get the full range output, and below and above that it gets attenuated. So yeah, now that the band pass is done, let's check out the band reject. So yeah, now moving on to the final analog filter of the four, which is the band stop filter or the band reject filter, and also they say notch filter. These are the three names. And well, band reject and band stop are basically synonyms. They mean the same thing. Notch filter is actually a kind of band stop filter. So every notch filter is a band stop filter, but not every band stop filter is a notch filter. So the vice versa doesn't really apply there. And I'll in just a second I'll show you what the difference is. But in general, this is the frequency response of a band stop filter. Same, you can sort of see it's the ulta of the band pass filter, which is between our two desired frequencies. The signal will be attenuated, whereas below that, and above that it will allow it to pass with whatever gain you want. So yeah, that's the main difference. And yeah, that's the part. Those two will be counted as the pass bands. This will be the stop band, and yeah, of course you'll have the transition band, because now we know, even via the hardware, as I've shown you, it's not ideal. You have all the dB gains, you cannot get minus infinity dB and all of that. So yeah, this is the response. And this is for a wide band basically. And another frequency response which I can show you is this. If you, as you can see, this compared to the older one, which had a much, you know, what can you say, it's not very steep, it's like slowly it's going and it's coming out, right? So the pass band is longer, the frequency, whereas the bandwidth, as they call it, whereas as you can see here, it's very narrow. So this is basically, you could say this is a notch filter. And there's a formula for it. I'll just show it to you here. It's basically based on the Q factor, which is known as the quality factor. And that depends on your center frequency and your bandwidth. So just for showing you, uh, the one which I'm designing here, if I just show you the circuit in multisim again, I'm designing it uh, uh, for these two frequencies. 4.5 kilohertz is our lower cutoff, and same as before. And 10.6 is our upper cutoff. So if we try and calculate this same quality factor using the formula, I have it here on the calculator. I've already calculated it. 4.5 kilohertz times 10.6 under square root, that is basically the formula for your center frequency. And the bandwidth is basically just minusing the two. So you can see our quality factor comes out to 1, which is quite low. And in order to qualify as a notch filter, it has to be greater than 10, as it's said here. So you can see this one is much lower. So this is clearly just, this is not a notch filter. What I am making is just a generic band stop filter. And similar to this picture, it has a wide attenuation band. Whereas if, let's say, we do something like 4.5 kilohertz and lower, and 4.5 kilohertz upper and 4.2 kilohertz lower. If you, as you can see, the stop is basically just, the bandwidth is going to be just 300 hertz, as opposed to what we have, almost 5 kilohertz right now. So if I calculate the same thing here, you can see 4.5 with 4.2, and yeah, minusing the same. Now you can see the quality factor comes out to be almost 14.4, close to 15. So this would qualify as a notch filter, and the response would look something like this. So yeah, just for clarifying that, that's how this will be. And yeah, now going back to the bandstop filter, yeah, the circuit is basically slightly different. As we saw in the band pass filter, we basically cascaded a high pass and low pass, right? But and you can sort of think of this analogy as like a AND gate, which means first this, then this, in series. Whereas for bandstop filter, you need something like a OR gate, so you have to think parallel. So here basically on top we have the low pass filter stage, and on the bottom we have the high pass filter stage. Both of them get a common input from our signal generator, the same signal. Both are depending on the same frequencies here, the R and C are chosen. And both are configured as just buffers, or there's no gain here, that's why I've just connected the inverting terminals to the output for both of them. And finally, in order to get our output, we need to basically sum these two. That's how it will be parallel. So that's why we have this final op amp configured as a summing amplifier, and to be particular, a non-inverting summing amplifier. So that's why the output of both of these go via resistors, just one case, to your non-inverting terminal. You can, this point is shorted and given here. And to set the gain, finally, since we didn't set any gain here, same as before, I'm giving this gain of 69, since it's going to be 1 plus RF by RI, and yeah, it's 68 and 1k, so yeah, that remains same. And this will be our final output. So as you can see here, we basically need 3 op amps, right? For our high pass and low pass, we got by with just one op amp. For our band pass we needed 2, and the 072 has 2 op amps, so we were fine. But now we need 3 op amps, right? So instead of using two TL072s, which is pointless, there's another one which comes, which is from the same family, the TL074. It's just a bigger version of the earlier one, and it has 4 op amps as it says in its name. So yeah, everything else remains same. All the CMRR, the high input impedance, it's the same GF80 op amp. Everything remains same. The slew rate is same. Just we have 4 op amps in one package, so I'll be using this one. And yeah, now that the circuit is done, I'll just go to the hardware and we'll see how the band stop filter is working. And yeah, we have the circuit here, and so now you can see the op amp is no longer the 8 pin TL072, it's the 14 pin, it's the TL074. So yeah, this is the low, as I can see here. Yeah, that's the high pass filter stage. The low pass filter is sort of hiding behind the wires. I don't think you'll be able to see it, but it's there. And finally this is the summing amplifier stage. So yeah, now I'll connected the final output of the third op amp to the oscilloscope. We'll see that, and of course the same two supplies are there as before, and we have the signal generator here. So I'll start with 1 kilohertz, which, and remember our attenuation band is supposed to be between 4.5 and 10.6 kilohertz, right? So let's start from 1 kilohertz, and we have starting at around 6.7 volts, and let's start increasing this. Let's maybe start going to 2. Let's increase 1 kilohertz, so 2. I'll start increasing. This is for 2, and 3, 4, and just before that around 5, which is close to 4.8. that is our lower cutoff, and you can already see from the earlier 6.7 we have come down to 4.3, so it's started rejecting it, attenuating. Now I'll start going to 6, and yeah, it's further, it's similar, 6, 7, and you can see it's sort of stuck at 4 volts. That's our attenuation part. And now going close to 10.6, I'll just go to 11, which is sort of close to 10.6, and I'll just change the time base, and you can see we are at 4.4, and you can sort of see a similarity, right? At 4 point around 5 kilohertz we had around 4.6 volts. Now we have 4.4, so that's basically the minus 3 dB point. That's where your attenuation starts and attenuation begins to stop. So now if I start increasing it towards 12 kilohertz, you can see now 4.5 and 4.65 for 17 kilohertz. For 14 kilohertz now we have 4.7, 4.8, and yeah, it's basically increasing, as you can see, 4.9. and yeah, let's take a final reading for 20 kilohertz, and we can see we have peaked at around 5 volts. So you can clearly see that in the attenuation band it dropped to almost 4 volts. Before, at the lower part around 1 kilohertz we had 6.7 volts, and now at 20 kilohertz we are at around 5 volts. So yeah, it's you can sort of visualize that we are getting this response. May not be exact, but yeah, that's the whole point. And as I said, this is just, we're using a first order filter, right? Just one capacitor. Second order filter will have a much better, the minus 40 dB per decade. It will have the slope, so that will be much better. So if you're actually using it for some application, second order or maybe even some other topology will be better. But yeah, for demonstration you can clearly see that we saw the attenuation at within the bandwidth of our band stop filter. So yeah, turning this off, that was the entire active filters series. That was all the 4 videos together. And yeah, analog, since analog is always the basic, it's always good to have your basics steady. That's when you can build upon them and do more complex stuff. So yeah, that was the end of the 4 filters. I hope you learnt a thing or two. We got to use the signal generator, which is very nice. And yeah, thank you.